Section 1.4, net force. Galileo determined that you had to push or pull on something to get it moving, but then it would continue moving unless something stopped it. Some kind of friction or some kind of resistance slowed it down. In physics, we call this push or pull a force. In order for an object to change motion, you have to apply a force to it. If the object is sitting still, if the object's at rest, and you push it, it's going to move. You're going to change its motion. If it's moving and you put your hand out, you can stop it. You apply a force and you change its motion. Throughout physics, we tend to draw images to represent situations. In this case, we represent things like force with arrows. Forces are quantities that are known as vectors. Vector quantities have an amount, but you can also assign a direction to them. If you apply a force to something, you can apply it forwards, backwards, up, down. And if you're trying to determine the force that it was applied in a situation, you need to know the direction that you applied that force. For example, if you're trying to stop a ball from moving, right, as it's coming towards you, then you have to apply a force in the opposite direction. If you applied a force in the same direction, you're just going to cause the ball to move faster. So the direction matters. And in many different quantities in physics, the direction matters. We call those quantities vectors. On the other hand, for some quantities, the direction doesn't matter. And we call those quantities scalars. Mass is an example of a scalar. You do not need to know the direction when you talk about the mass of an object. In fact, it doesn't even make that much sense. When a friend asks you, what's your mass? You say 25 kilograms left. Just hearing it is silly. Those quantities are known as scalars. Science is full of mixtures of both, and we will discuss more of each throughout the rest of this course. We use arrows to represent vector quantities because arrows can point in a direction, and that gives us the direction. But we can also change the length of the arrow based on the magnitude of the vector, based on the amount. For example, the greater the force, the bigger the arrow. The smaller the force, the smaller the arrow. If we have multiple forces on an object, then we can combine all those forces together and determine what's known as the net force on the object. And the net force is just the sum of all the forces on that particular object. And that net force is going to determine how an object moves or how its motion is changed. Net force absolutely depends on direction. So as you can see in the image, in the first image we have two forces applied to an object. Those two forces are both pointing to the right. They're both 5 newtons. And so those two forces are going to combine. You and your friend are, behind a car pushing it in the same direction. Those two forces are going to combine and add up. And in this case, the net force on the object is going to be 10 newtons to the right. If those forces oppose each other, but are still equal, so you and a friend are pulling on something from both sides, then the net force on that object would be 0, and the object won't move, or it won't change its motion. So the direction matters. And the magnitude matters too. If one person is pulling with a greater force than the other person, as you see in the third image, then you will still have a net force. However, it is the difference between the two forces. So if a person pulls to the right with a force of 10 newtons, and someone pulls to the left with a force of 5 newtons, the net force on the object is just 10 minus 5, or 5 newtons.